So this was the application of the greedy approach by the name of optimal merge pattern, and one of the applications has been used by the Hoffman for doing the data compression using the logic of the optimum merge. So as we said that two types of coding could be possible. One is the fixed length when we don't need whole of the character set from the ASCII. We develop our own codes this way. There the compression takes place in our message transfer. And that we saw yesterday how that is done. And today we will be dealing with the variable length code. The message will be same which we took it yesterday of 20 characters from A to E. So the variable length code, which is the actual proposal put forward by this Hoffman, and the same thing variable length coding is also known as Hoffman coding, and it follows this greedy approach of optimal merge. So again, the message, as I said, will be taken the same from A to E, and we will count the number of times the particular character gets repeated in this message. And this again, we have done it yesterday. The character A, for example, gets repeated 3 times, so we will update its count to 3. The character B accordingly repeats in the message 5 times. So the second column in this table will be dealing with the number of instances each character gets makes visible itself in the original message. So what this Hoffman coding says is that we will take these counts of every character, that this A is repeated 3 times, this B is repeated 5 times, C is repeated 6 times. Like we did in optimal merge pattern, we will arrange all those characters here in this one. That is the leaf nodes of this tree according to their ascending order. So initially the E gets repeated the minimum number of times, which is equal to 2. So it will come firstly, then the next character which gets repeated a little bit more number of times than E, that is character A. From this table it gets repeated 3 times. Again similarly, then character 4D, which gets repeated for 4 times, character B and C, which gets repeated for 6 times. So we will arrange them in a row-like fashion based upon their ascending order. And now from here, we will start the greedy approach of merging, but using the optimal greediness. So what we yesterday discussed is that as far as optimal merging is concerned, we get the minimum merging cost only when we merge the minimum 2 initially. So among this list, we will take the least minimum, which are the 2 and 3. We will make it as a pair, 2 items, 2 and 3, and we will merge them. So this will be the first step. 3 plus 2, it will give 5 after merging, means this new list will now contain 5 number of elements. So now we have reached to this position. We are having this 5 node and the remaining 4, 5 and 6 node, because those 3 are yet to be merged. Now among those 4 nodes, that is 5, 4, 5, 6, which are the least in size. So either we can merge these two or we can merge that this and this. This is same thing. So when we take this list and this list and make it as a pair, so 5 plus 4 will again add up to 9 and we will reach here. So now in the table or in this array, we can say the number of nodes we are having left is 9, 5 and 6. So again, we have to take a pair, and pair should be according to the greediness approach, the minimum one. So 9 is greater than both of them, so it won't participate in pairing. 5 and 6 are minimum, so they will merge and will add up to 11, which will become a new node. And finally, we are left with 9 and 11, the only one pair, and we will add them up to 20. So we get a tree type of structure after using the optimal merge pattern for joining those different characters. And then the Hofmann says that in this tree, every right arm or every right edge needs to be given one weight. So in this tree, this is the left subtree, this one is the right subtree. So every right edge. So in this tree, we are having two branches. One is for the left, another one is for the right. So every left will be given a weight of 0, and every right arm or right edge will be given a weight of 1. So here it will get 0, this will get 1, this will get 0, this will get 0. But since this one is the right of this 5, so it will get 1. This one is the right of 9, it will get 1. This one is left of 11, so it will get 0. This one is right of 11, it will get 1. So now to develop code for every character, simply we have to traverse these left and right branch. For example, for A, character A, which was repeating itself 3 times in the original message, we will directly start from the root node and will traverse this tree in order to reach this A. So the number of edges or the type of data we will get in between traversing from root to this leaf node will be the code of this character. So for A, if we start from this root, this will be 0, this will be 0, and this will be 1. So A will be coded as 0, 0, and 1. Similarly, for B, we will traverse from root to its leaf node. This will be equal to 1. Then we are going to the left side 0, and B will be coded as 1, 0. Okay, and accordingly E, if we see the E is here. So starting from root node 0, 0, and 0. So E will be coded as 000. So now in place of fixed length code where we were giving a same length of code to each and every character, we are changing the pattern and logic where we are giving the least number of codes to the character which is repeating itself maximum number of times, because this is the greedy approach. And we are giving a little bit more number of bits as code to the character which is repeating less number of times. This way it becomes an optimization problem, a greedy problem, and this way the Hofmann puts out this application of this optimal merge pattern. And now we see that the original message we were having of 20 characters was like this. And when we developed this Hofmann coding for every character, the B will be sent like 10, it will be sent as 11, it will be sent as 11. Accordingly, every character will be now transferred from source to destination using this code as a benchmark. So in order to find out the total number of bits we will be transferring, if we have to transfer this message, we will see the individual number of bits we will be needing for every character. Since A we are coding as 001, so for one A character we need 3 bits like this, and this A is repeating 3 times, so 3 into 3 will be 9. That is the total number of bits we'll be needing just for representation of A. Similarly for B, as it repeats 5 times and we are coding it as 10 using the Huffman coding, so 2 bits are needed for this B representation and it gets repeated 5 times, so 10 will be needed in total for representing this B. And similarly C, D and E. E, since it's repeating 2 times and every one of its repetition needs 3 bits, so 2 into 3 6. The total number of bits is the addition of all those, and that's equal to 45 bits. So we need only 45 bits to transfer this message from one station to another. Now the size of this message needed will be 45 bits, but as again said it yesterday, that in addition to sending this message, we need to also send this table to the decoding size so that it will be able to find out how to decode this. So in addition to transferring the 45 bits for this message, we need the chat also, this table also to be sent. And in this table, one thing we need is the character set, and these are 5 in number. So 5 into their respective ASCII code, that's 8. 8 into 5, which is equal to 40. And similarly, we need 12 bits for code, because this is how much? 1 2 3 4 5 6 7 8 9 10 11 12. Okay, 12 bits will be needed for code to be sent to the decoder. And in total, if we find out the total size needed for this message, including this message, the table and the code, it will be sum of all those 45 plus 40 plus 12, and that comes out to be 97 bits. And when we compare this one with the fixed length, it was 115 and it was about 160 bits without using any compression technique. So this is actually the benchmark. This is the logic behind this compression techniques, how it uses the greedy one. And this 97 bits could be also found from this tree which we have made here, and the formula is summation of di into fy, which means fy means the frequency of every character, the number of times it repeats. For A, this will be equal to 3, and distance means its distance from okay, yes, we are calculating it for this thing. Okay, so suppose this 2, okay, this is the value of this E, okay, and this 2 is distance of how much from the root? 1 2 3. So this 2 into this 3 plus this 3 which is for A, this A, 3 into 1 2 3 plus this 4 into distance, it is far away from this root node, 2, plus this 5 into 1 2 plus this 6 into 1 2, again 2. So summation of all those will again give you the total number of bits which is needed for representing this message. So in both the ways we will get the same result. So I think it will be clear to everyone. So we will stop it here, and we will now shift ourselves to the another design technique, which is divide and conquer. Because the greedy approach, we have been traveling for quite a while. Now we will see another approach of algorithm designing, that is the divide and conquer. We are having a big problem whose solution becomes hard for us to find. So what we do is to divide it into small chunks, small size problems, which become manageable for us to solve. And when we find the solution of little problems, we combine that solution, and that we produce as a solution for the original big problem. This is the only logic behind this divide and conquer. And you might would have seen a lot of examples of this technique in our daily life. And the most technique which was being used by the English people during their, during the times they were conquering the world. So this is the original approach, that a problem which is of size n, and it becomes difficult for us in its original space when its size is n. So we divide this problem into different steps from 1 to n or 1 to k, and we found solution of every subproblem from S1 to Sk. Then there we have to develop a means to combine these sub-solutions, and this sub-solution after combining becomes the solution of the original big problem. So the algorithm is simple, that two conditions are there. If problem is small itself, if problem is not big, if it is small itself, means if it is only one element. If there is only one element which we need to solve, which means it is a small problem, and we just take its solution, whatever it is. But if it is greater than 1, 2, 3, 4, whatever, we divide it into small chunks. Dividing, finding the solution of all the sub-problems, and returning back and combining. And you might would have seen, we have taken a detailed example of this technique when we studied the binary search. Yes, whose complexity was log n. In place of linear search, we were dividing the array into two halves, finding the mid when the array was in ascending order. Then we were recursively calling this section, recursively calling that section. Again, this section we divide into two, again that section. So that is one example of this divide and conquer approach. And that's why in bold lines I have written here that divide and conquer approach always uses the recursion for solving its task. And again, one more thing to be noted is that these sub-problems should be again of the same context which the original problem is. Like the original problem was to use the binary search, the sub-problem should also be of the same. It should not be like the sub-problem will find the maximum and the original will find the binary search. That is why both the problems should be of the same nature. So the general recurrence relation for such an approach is when n is small, means when n is only 1, we take it as g of n, and when it is equal to greater than 1 or the problem is big, we divide it into sub-problems and take their respective times and summation. And then again we add one more term to it, because this term is needed for doing the various divisions of problem P into sub-problems and combining the sub-problems into original solution, the extra time which it will need. So this function Fn will represent both of those, dividing plus the combination. And the general recurrence formula for divide and conquer algorithms is written in this form, a general form. And you might would have seen we solved such type of problems also, the dividing functions, using various recurrence techniques. Even the master's term took the value of a and b and try to find out in which group it is. So different type of divide and conquer algorithms we'll be seeing is the binary search, maximum minimum finding, the merge sort, quick sort. These are all the various kinds of divide and conquer algorithms. We have studied some of them and we'll be studying some of them while traversing this whole approach. So just a quick reminder for binary search, which is recursive in nature, because if it is divide and conquer, it should be recursive. So we are finding a value mid or the element which we need to search. We are saying if it is less than a of mid, which means it will be on the left side of the array. So we recursively call the binary search by decreasing the low and high. Else it could be on the right side. Again, we call the recursive binary search and go to the right side. So means we are dividing when there is an array of 20 size. In the first step, we will take the mid value, divide it into 10 and 10 half. Okay, P is divided into P1, P2. Then P1 will be again recursively called. It will be divided into 1 to 5, 5 to 10. So this is how the divide and conquer logic applies in the binary search case. So iterative, we have implemented that. It's not a big deal. Now, yesterday's lecture, we discussed about the concept of merging. And to understand the first algorithm in this merge, in this divide and conquer, which is the merge sort, makes it compulsory to understand merging. And merging, we discussed it yesterday. That's why I kept the yesterday's topic and today's topic in sequence, because this will be quite young in our minds. We are having two sorted list or sorted array, A and B. And we need to merge them in a third list C so that this order should be maintained in the ascending order. And yesterday we discussed that this is sorted, and we merge it into another one using this code, using this algorithm. That we compare the first element of A with first element of B, and whatever among them is minimum, we push it inside the C. And C value gets incremented, means next in memory location it is pointing. And the one among those A and B, which has been pushed in the C, that will be again incremented. Then the diagonal element will be compared. Suppose here 3 was smaller, so 3 will get pushed in the C. Now I will get incremented to 8. I will now point to 8. So now in the next turn, 8 and 5 will be evaluated. And 5 is lower, so 5 will be the next element to be pushed in the stack, or sorry, array C. And this way we will reach to a point where finally 20 and 11 will be compared to each other. So the minimum is 11. Yes, and 11 will be pushed. So again, we will reach finally to a point where either in A or B, one element will remain, which will not be having anything to compare with. Simple. And for that, we use this code that if any element in list A remains individual alone there, just take that element by incrementing this K to the next memory location and push that A of I there, if it is A of I. If it is not A of I, then go to B. See if there is any alone element present in the array B. Push that in C. So this kind of, when we are having two lists or two arrays sorted, and we need to merge them in a third list also in the same order, this technique is known as merging. Simple. And when we are having two lists to be merged, we call this merge pattern as two-way merge. When we are having two sorted lists to be merged, this is known as two-way merging. But in practical applications, it's not necessary that we should be always having two lists to merge. We could be having 3, 4, 5, 6, 8, 9 m number of lists to merge. And when we are having m number of lists, A, B, C, D, E, F, and we need to merge all of them in a final list in the same order, that is known as m-way merging. So the merging could be of any order. And whenever we talk about the merge sort, we will be merely talking about the two-way merging. So, okay, this is again the same code here which is written how we do the merging. Now, an example is taken here. First of all, before going deep into this example, there are two types of merge sort. Like for every algorithm, we are having two approaches. One, we deal with using the for looping or any looping, which is iterative. The another one is when we keep on calling the recursive functions. And whenever you see anywhere two-way merge sort, this two-way merge sort is not that which I said in this previous slide. Two-way merging. It does not always mean that there should be only two lists which you need to merge. Two-way merge sort. Two-way merging is different. Two-way merge sort is different. That is two-way merging, means only two lists. Two-way merge sort is when we are having, when we merge, when we sort the data according using the merge sort, but in an iterative manner. When we use the merge sort iteratively, that is two-way merge sort. And when we talk about only merge sort, there is no two-way. When we talk about only merge sort, it means this is a recursive merge sort, divide and conquer. So you might would have seen, we always discuss about the merge sort, because we are interested in the divide and conquer approach of this sort. That's why that is known as merge sort, which is divide and conquer. So we are giving an array A of 8 elements from 1 to 8. And we are being asked to solve this array and arrange it in sorted order. And arrange in sorted order means we will use this two-way merge sort. We will not use divide and conquer approach. We'll see how we will solve it. The first pass will be that we will compare these two elements. I mean, there could exist many ways. We can, like we did it yesterday, optimal merge. We can start from here, we can start from here. So this is just for the example purpose to go into the actual merge sort. So in the first pass, what we can do is to compare those first two elements and sort it 3 and 9. Similarly, the next two elements will be then sorted 5 and 7. This all will happen in the first pass. So this individual element will be taken as one list. For example, as an assumption, we will take the data at memory location 1 as one list and at memory location 2 as another list. So this will become a two-way list merging. So we will treat it as two-way, and two-way merging we do 3 and 9. This will be taken these two as two-way merging 5 and 7, two-way merging 4 and 6, two-way merging 4 and 6. Now we are having, in place of those 8 elements, we are having 4 elements. Take it as 1, take it as 1, take it as 1, take it as 1. So we are having 4 lists now. So in the second pass, we will take again these two lists and we will sort them 3, 5, 7, 9, because we are treating it as 1, we are treating it as a 1. Similarly, in this pass, we will take these as two lists and sort. Then in the third pass, we will take this whole as a one list. It is sorted like we discussed in the example yesterday, today also, this is also sorted. And these two lists will now become just like these two. Yes, sorted AB with 4 elements, sorted B with 4 elements, and we need to put it in C. So we will put it in an array in a sorted order. that will give the final array like this. And either we can store it some other array, or we can put it back into original array A in the sorted order. So this way we are able to accomplish the sorting, but using two-way merge sort. Two-way merge sort means which is not divide and conquer, or which is sort of iterative. We don't call recursive functions. Now you see at each, here at pass 1, we were having n elements. N is equal to 8 in this case. So here at pass 2, again, we were having those 8 elements. So in a general case means n elements. Again, here in pass 3, we are having n elements. So all the passes are having n elements. And again, if we see that, if we find out, this becomes a kind of, again, tree structure. We are having 8 elements, we go to next level, we go to next level, we go to next level. So this is root, sub-branch, sub-branch, sub-branch. So how it decreases is that initially we were having 8 elements, 8 or 8 different lists, you can say. This is a list, this is a list, this is, so 8 lists. We go to the next level and we divide this 8 by 2. So we are getting how much? 1, 2, 3, 4, 4 lists now. Now again, that 4 is divided by 2. We get only 2 lists in the next level. That 2 is again divided by 2. We get 1 list finally. So for how many times this will go? When 8 will be divided by 2, 2, 2, 2, finally it will become equal to 1 when we get only 1 list. So this can be also written as 8 divided by 2 power k. Okay? 8 divided by 2 power k is equal to 1. So our k will be equal to log of n. That will become the number of passes. So using simple logic is using this two-way merge sort for sorting any array. The number of passes you will be needing is equal to log n. Log n means the total size of the array. Here the size of array was 8. So 8 log 8 to the base 2, that will be equal to 3. So 3 will be the number of passes needed for doing the complete sorting of this array. So this could be also a kind of question being asked. Simple. So 1 pass, 2 pass, 3 pass. And for n, since we are having those n data elements at every time, so the total complexity will be the size or the number of passes and the n elements, n into log of n. And we have seen the complexity and log n in our lecture also, in our recurrence relation lecture. When the recurrence was of this type, AT, this one, its complexity was equal to n log n. कितना हुआ टाइम? Okay, we will discuss about the merge sort. So this algorithm which we wrote here, this was for merging, and which is a prerequisite step to understand how actually the merge sort works. And merge sort is what? The divide and conquer implementation of the sorting algorithm. So now we go to the actual merge sort, the one we are interested in. So if we look to the pseudocode of this, we are passing 2 parameters to it. Low stands for the first element of the array which we need to sort. High will be the last one. And small p, we say that this could be a small problem if there is only one element in the array, as I said. More than one, we will treat it as big, and any big needs to be divided. So when it will be big, when low is less than high. If low and high are same, means there is only one element. And in that case, it is a small problem. If there is more than one element, it is big in divide and conquer approach. So we will divide it into sub problems. How? Find a mid that will be low plus high divided by 2. And when we found this mid value, we will recursively call merge sort again. And the parameters passed will be low will be again the same, the left hand side array. And now its high will be treated as the mid. That is the left array. Similarly, another merge sort will be recursively called for the another array on the right side, and its high will remain unchanged, but its low will change to 1 plus mid. Hmm? Yeah. And when both of those merge sorts are called, finally we need to do means this merge sort first one. It will return me the elements in sorted order on the left hand side of the array. Yes, this one. And another merge sort will give me the sorted order of elements on the right hand side. So 50% of left hand side is sorted, 50% is sorted on the right side. Now I need to call merge algorithm, merging. Merging is this. That's why I discussed it initially. So when left hand side array is sorted, right hand array is sorted, we call this code merging. And it will then sort it in the third array or in the same array in the original order, which will be the sorted in nature. Okay, and this is the logic behind it. So now you see we are having the same example as we took in the two-way merge sort. The only pattern is that we are changing the logic. So traveling around this pseudo code, we initialize low to 9, which is the first element, high to this 8, the last element. And the first step will be that if low is less than high, the condition is true, so it's a big problem. Divide it into small problems. And how we divide is find the mid. Mid will be low plus high, that is 8 plus 1, 9 divided by 2, that will equal to, that will give the memory location 4, not element 5. So mid will point to it. So you want to finish it today or some other lecture? Hmm? Okay, we'll stop it here. We'll discuss it another lecture. Yeah.